Hello everyone! Welcome to another stream talk about software engineering, and today I'm going to talk about different stuff we have with software engineering, and there will be no code, only pictures and my considerations. The topic is too broad, so I cannot cover it all, but there are mm, some points I would like to make, because software engineering, it's essentially an area, I would say a discipline of human activity that exists in nature, but it seems it not many people do it, right? Not many people do it uh, following some knowledge. Mostly people do it intuitively and not often correctly, because you can write code and build systems in many ways. Most of those ways, millions ways, will work, but will have many various issues. And it's a big question, a huge question. Is it possible to build a perfect system? Does its system exist? Whether it's possible to create a perfect system? Maybe what we do in the conditions where no perfect systems can be even made. All the systems maybe are not good enough from some point of view. But software engineering is our tool to navigate between different opinions, solutions, and ways of doing stuff so that we could achieve our final goals. We don't really need a perfect solution. We need a solution that solves our business tasks. And therefore, software engineering is inherently pragmatic discipline. It aims to achieve results. And there are some recommendations how to do that. Those recommendations save time for developers, provide ready solutions and reasoning frameworks so that a person could sit and solve tasks instead of doing research, instead of reinventing the things. This is cheaper for the business, having already solutions. And software engineering, one of those solutions, I would say, reasoning framework that could help. Again, there is no specific uh, uh, discipline or maybe a set of rules everyone will agree. There is even a huge computer science and software engineering area or field of research, and two of them actually, right? Software engineering and computer science. And I guess it is not as coherent as mathematics, for example, because software engineering is not mathematics. It's mostly an experience based discipline. So let's move to the topic itself, right? I want to make a point that knowing those principles and approaches of software engineering shortens the path to the final goal, knowing how to build software. And in functional programming, for example, we kind of suffer from insufficient knowledge about software engineering. We have a lot of hints from mathematics, and functional programming is more mathematical than imperative and OOP programming. But those hints, they do not represent a pragmatic view on how to build an application from end to end. At least it is so at the moment. You can certainly use those insights and smart things to enhance your development in functional programming, in functional languages such as Scala and Haskell, for example. Maybe you will achieve a good quality of your separate piece of chunk, and you might want to have many of those chunks like libraries for this or for that, maybe some tools. But once you start combining them, this glue, it doesn't fit into any mathematical concepts yet, because mathematics provides many notions that could be in principle used as this glue and could constitute the idea of software design for some functional programming, but it hasn't yet done. It's not expressed as a comprehensive methodology. For example, there could be a methodology, I believe there could be a methodology that uses category theory as this kind of glue between different parts. And the very idea how to combine those parts without sacrificing complexity, simplicity, without sacrificing simplicity, should be also researched. But for now, I think functional programming doesn't have this comprehensive methodology of doing things with mathematical approaches, only separate parts. You can develop libraries, you can develop small chunks of your code, but how to model the domain with category theory, for example, abstract algebra, maybe you can. How to architecture your application, maybe you can. Still, it's a hidden knowledge. Maybe there are gurus who know that and they do not share this secret knowledge with us because it's a source of appreciation, right, for them. And if they share this knowledge, they may lose that superpower position they have for now. But so my point is we need that. We need software engineering and software design disciplines for functional programming, because in OOP we already have that. We have a lot of things in there, and those things help people to do stuff, especially especially on the higher level of software engineering, like solution architecture, security issues, and etc. etc. Sometimes on the application architecture level, the higher you are going in this ladder, the more you need knowledge, because you cannot just invent things on the solution level. You have to reuse many things that exist. You can reinvent things while coding, right? You can reinvent implementations and interfaces eventually. But once you climbed upper on the solution level, on the enterprise architecture level, you will have to use many existing things, and you will need to know how to use them. Well, yes, so we have many levels of software engineering, and those levels have own approaches and ideas. And functional programming, object-oriented programming, those things start matter maybe on the application architecture level, maybe even on the solution architecture level, because you can in principle call service approach as something object-oriented, right? You have microservices which can interact with each other, and why not call them objects or classes? This can be in principle seen as object-oriented programming, maybe design, and maybe those as microservices can be considered actors on this level, on the level of solution. And actors is it's a OOP by Alan Kay definition. So maybe those things have some distant relation to solution architecture, and you can probably build a reactive streaming architecture of the solution using functional ideas, right? Yes, but mostly those things paradigms do not apply to the high level of software engineering, and they start mattering on the level of application architecture and code. And on this level, we can talk about functional programming and object-oriented programming, or maybe we should start talking about styles of programming, because the paradigm as a concept is not yet meaningful today. All the languages have many different styles, support many different styles of programming. All the mature languages, for sure. For example, C Sharp, it supports functional programming as well as object-oriented programming, as well as maybe aspect-oriented programming or something like that. So languages support many different paradigms, and the mix of those paradigms constitutes modern code bases. Yeah. And if we still stick to the idea of paradigm, we can talk about different approaches to reason. This is a reasoning framework, or maybe even software engineering as it is. I've been showing this picture many times, but anyway, so on the upper level of this reasoning framework, we have methodologies. Following methodologies helps us to build better systems, at least in theory, but actually from my experience, they really help to build systems in practice. It's not just a theory, it works. So on the upper level, we have, for example, object-oriented design. And it can have own general principles, right? High-level solutions, and then implementation details follow. The same reasoning can be applied to functional programming, to type-level programming, and for some time we didn't have a methodology in functional programming, and we could only borrow the way we code from OOP, or we could reinvent our coding practices in FP, but those were like secret knowledge. So I decided we need such a methodology like object-oriented design, but for functional programming, and I created it. I called it functional declarative design. Same as type-level programming. Type-level programming is around here for a long time. C++ has templates. Templates are super good, super useful. Well, good maybe is a brave word, but super used in the industry, in the C++ world. There is a Boost library which is massively templated. So type-level programming is here for a long time, and people really love doing that. But in Haskell, I would say we have a lot of type-level features, or really difficult ones, and again, we don't know how to combine them to achieve concrete results. Maybe some folks can just play with types and achieve those results. But this is, again, not a knowledge, not a system of knowledge. It's a folklore, or maybe wisdom of separated individual isolated ideas. So again, I decided I need something like that and started inventing pragmatic type-level design as a methodology. What items, what points can we put into those methodologies? Well, first of all, we should state that software design as a part of software engineering is an activity, right? Is an activity to build something with predefined or maybe desired properties. And one of those properties is absolutely significant. It's complexity. Complexity should be low. We should strive for keeping complexity low. For that, we have many tools, such as general principles to follow, like inversion of control, solid principles, and modularity, purity, all those cool things that help us to structure applications in a correct way. And certainly we can use high-level solutions such as architectures, such as interfaces, both OOP and FP. Those are super important to separate things and to divide and conquer, right? To divide our application and code into separate, isolated, individual, independent parts, so that the code that uses them could be free from implementation details. It could be simpler in this regard. And this practice is not only OOP practice. This should be used everywhere we need it in functional programming. And actually, functional developers use different functional interfaces. Sometimes they didn't even think about what they're doing, but actually they were doing a normal software design with interfaces. Those functional interfaces, we have numerous of them, various of functional interfaces with various properties. Yeah. And there are many other tools that help us to build solutions. So this what can be a part of our methodologies. Maybe we can talk about those methodologies a little bit deeper, not deeper, but a little bit more granular. So there are design principles. Not all of them are here. There are more design principles, and the previous stream was about design principles. So you can watch it, and you will see how many of them. There is a slide here actually. Also, we used to do requirements and modeling with UML in object-oriented design. From my experience, it's not always a very convenient tool, because UML is a very rigorous, I would say, strict and maybe too rigid structure, too rigid approach. UML stands for Unified Modeling Language, right? It's a set of various diagrams, maybe 10 of them, or maybe even more, various diagrams for various designing and modeling purposes. In particular, class diagrams. It is not a very convenient way to brainstorm the domain. For example, you need to design something. You would naturally write some code, or maybe draw some general shapes like rectangles, maybe circles and arrows, but it's not very convenient to design with class diagrams. Maybe with some help of the tools, drawing tools. But anyway, from my experience, they better serve the purpose of knowledge transferring. Once you have some design, you implemented it, you described it in text, and also demonstrated it in class diagrams. It's much easier to understand your object-oriented design with class diagrams. There are many other diagrams more or less applicable to OOP, more or less applicable to FP, and this was our maybe not primary but very widespread tool for modeling. There are various architectures in object-oriented design. I'm not sure, maybe it's not even the full list here. Layered, onion, hexagonal architecture, various plugin-based architectures, maybe some architectures from game development, they have own approaches. There are architectural design patterns for graphic user interfaces, for example, MVC, MVVM, and so forth. There are many things developed for object-oriented languages. Partially, those things can be applied in functional programming. Maybe we need some general reconsideration of those terms in the functional programming settings. Yeah, and there are development tools for sure. This is an example of class diagram. As you can see, we can define properties and methods and classes and relations between classes, inheritance, abstract classes, many things. UML class diagrams are very regulated. This is a sequence diagram. In general, it's not that bad. It can be used to understand how an object lives, what is its lifetime, and what subsystems it touches. I personally did both of them. I did much modeling with UML. doesn't feel very convenient today because we live in a world, in a very fast world. Email is slow in general, all right? But still, sequence diagrams are more or less good for what they are doing. Functional declarative design, again, those 4 columns. Design principles, yes, we have design principles more applicable to functional programming, especially functional programming with static types. And we need those things, and do not think that solid design principles are about OOP. They're about any software engineering, and actually they can be probably applied to other engineering fields like electric circuits. Yeah, we were talking about, we've discussed design principles previously. Requirements and modeling, it's another story. There are data flow diagrams, for example. You can use them to show reactive and stream models, which are functional models. Maybe I need to put another rectangle here. You can use those streaming models to naturally reflect what you have in functional code. The match will be quite big. I mean, there is a model and the code may look like that model and vice versa. There will be a small gap between them, maybe only a syntactic gap. I personally prefer mind maps for requirements collection and various concept maps for brainstorming and modeling. But actually, we mostly model with coding, right? We also have various architecture design patterns and approaches in functional programming, such as functional reactive programming, FRP, rope, which is railway oriented programming. This is actually an either monad re-implemented in the F# setting. So it helps to control a happy path and an error path and combine them with combinators, which is what the either monad does. It's the same idea and mostly the same implementation. There are the Elm architectures, 3-layered architectures, and etc. etc. So we have a lot of stuff here. And of course, there are interfaces, design patterns, and idioms. This is a mind map for Minecraft, how it could look like. It's a really very convenient tool for doing requirements collection. And this one is another concept map, maybe not very structured, but this is intended. I do some brainstorming here. I am trying to research what subsystems I need in my application, so I put those in just rectangles, nothing more. And yes, we were talking about design principles. Many of them exist, and most of them universal, finally applicable to OOP and FP, and maybe with some changes, with some specific adaptations, but still they are very important and can be used, right? I would say the era of application frameworks has never ended, as some Haskell said in 2020, sorry. And application frameworks constitute a part of software engineering because they essentially simplify development. You do not need to invent things. You can take some framework and continue developing. It's Ruby on Rails. It's a framework for building web applications. Zio from Scala. It's a general purpose backend framework, right? Maybe it has something for front end, I don't know, but anyway, it's a framework. There is HP in Haskell, there is Rio in Haskell, and maybe some others. You can see them here: Hydra, Node, OLHS, and many others. So frameworks do not going to go. They will be with us for forever, I guess, because it's a ready solution. You do not need to reinvent things application frameworks provide you for free. So this is a very important part of our development. Maybe not very creative. You may feel bored by programming with frameworks. There is no freedom of expression. You are constrained by the frames of that framework. It's called framework, right? It's a frame, it's a foundation. It comes with some philosophy of development, and you follow that philosophy. For example, Ruby on Rails has a very strict structure, and you need to follow that. And sometimes it's good, but in functional programming, it seems folks love freedom, and they love freedom too much. Freedom of expression, especially in the presence of mathematics. They absolutely in favor of doing mathematical research for regular development, which is not often a good idea because it's difficult, takes time, and complicates the code. Yeah, a couple of words about architecture and what kind of architecture we have. Mostly in Haskell, for example, we use free-layered architecture, or maybe we can say those layers can be supplemented by other layers, but those layers are the main, like domain and business logic. Two layers actually, right? Here, interfaces and EDSLs, it's a services layer, and implementation and runtime, it's an implementation layer. Also in functional programming, we can see our application as two-layered one with pure and impure part. Mostly this is true for all programs in functional languages. It's sometimes implicit, and mostly it's implicit, but sometimes it's explicit, like in Haskell. Maybe the Zio framework allows you to have explicit worlds of purity and impurity, but in Haskell those two worlds are separated by the IO type and IO monad. So it's another logical division by layers. We also prefer doing various domain-specific languages, especially in Haskell, because it's very convenient for that. My point is that EDSLs are a little bit underrated as a tool of software engineering. It's a super tool for doing domain modeling and for beating complexity. Yeah, I cannot even be grateful enough to this approach because it saved me so many times when I had a difficult domain and I needed to structure it, and I struggled with the current approaches. Those were not domain-specific languages, but some arbitrary code, and you do not see the domain behind this code. And I tried to re-implement that thing using some EDSL, and everything started working. And this happened many times when embedded domain-specific languages helped me to do my work better. Also, another point I would make is that we can call everything to be an EDSL if this set of tools, maybe set of notions and concepts, small concepts in code, relate to some specific domain. For example, there is an EDSL for networking. In here, you have connect, listen, close. Those things represent the domain of networking. And functions, therefore, can be considered embedded domain-specific language. In functional programming, we have more of this. If you open control monad, there is a specific language how to deal with monads, with general monads, not specific one, but all monads. Any monad you want, those functions will work for this monad, and the code will look the same for every monad. In it's a generic programming, right? And the more we go to the generic level, and Haskellers love doing that, and Scala developers too. The more we go to this generic level, the more strange concepts emerge, like concepts from abstract algebra, from category theory, more from type level programming. And those things certainly require a specific set of knowledge, specific set of skills to understand it. And if we were programming our applications with such language, such approach of mathematical concepts, it would be really difficult to embark into that project, to learn it, to navigate, because the higher you go, the less you see the business under your code. And unfortunately, this is kind of a plague in functional programming, I would say in Haskell. We as functional developers, as Haskellers, love doing this stuff rather than business stuff. And our languages, especially our libraries, start looking like extraterrestrial writings. Some texts aliens sent us, and we are in complete misunderstanding what those things do. And this is certainly complexity. This is accidental complexity that we should keep low in our programs. So even though embedded domain specific languages fight with complexity, there is a way to complicate embedded domain specific languages themselves, which is not a very good idea. Unless it's an okay idea if you do library development, right? But it's not okay for regular development of regular applications. Yes, just a minute of fun. This is a list of various concepts from Haskell. Those concepts exist in libraries in number. Can you spot something that does not relate to this list? Some personal disorder. Maybe you can even type in chat, because I'm curious. Can you spot those strange things that do not relate to programming? I'll take a pause and drink water a little bit. I need more water. So, do you have ideas? Well, all right. Maybe we will return to this slide later, and I'll show you what was wrong with this list. All right? Or you can type your answer in the chat. Well, actually, this is kind of the end of my presentation. Again, today I wanted to express my concept of software engineering, but books express it better. And for object-oriented programming, we have hundreds, really hundreds, maybe even thousands, maybe hundreds of cool books, very nice books about various aspects of software engineering. I would personally learn and improve my knowledge in higher levels of architecture, in particular solution architecture, enterprise architecture, and other kinds of architecture. because I call myself architect, but mostly my knowledge is related to application level and a little bit solution level architecture, because this is what I need at the moment as a book author. But I really want to learn more of this. I would like to know more about CQRS approach, which is uh, command request segregation. I don't remember. It's the approach to separate requests and writes of the system. You can write something into the system and request data independently, and you need to organize that system in a certain way. Mostly they do event sourcing for that. When there is no notion of deletion, you do not delete data, but you rather update and insert new data, which is called event sourcing. And the architecture that is based on collecting events and building a model from those events. I personally did that, and I had an experience with that. I don't. There was a telecom company, and we needed to collect and build data for payment for our clients. So I, with my co-workers, created a system where we could write things into a database, and we could create snapshots of that database, and nothing should be deleted from that. If we need some update, we write an update row, specific type of row into the database. We append data for deleting or for updating, and then we can produce snapshots and can rebuild models at any moment. This is an interesting approach. I would like to know about that more. I also would like to know about reliable systems based on messaging. For example, messaging using message brokers, right? Or maybe using reactive approaches such as streams. This is another topic that combines the properties of software architecture on the solution level and on the programming level. So yes, there are a lot of things which we can learn and improve our knowledge. Well, in functional programming, we have a specific problem. I would say even a specific focus or maybe passion about correctness. And correctness, it's an important topic, but this topic is too vague to talk about it seriously, because correctness from science point of view, it's a way to follow, not the way, but the mandatory to follow some specification. If you have a specification of some code, you need to encode it as close as possible using various techniques that help your application to work, especially techniques using type level programming and generic programming and provers, mathematical provers. So there is a specific area of software engineering that is revolving around correctness. It's mostly scientific term, but we as software engineers, pragmatic software engineers, understand correctness not as a correspondence between a specification and the code, but rather as a meaning of the domain. If the meaning is implemented correctly, as we see it, then everything is correct. We can ensure about that not using proofs, because proofs are expensive, and doing mathematical proofs and using formal verification is super expensive and cannot be done for all the aspects of programming. But we can ensure our code correct in our engineering meaning by using tests, which is another huge topic of software engineering, right? Tests and the principle make invalid states irrepresentable, which is another good strength of functional programming, actually. So at the extra set, object-oriented programs are offered as alternative to correct ones. So he didn't like OOP, and this is not, well, maybe he did like, but this quote says he didn't praise the OOP that much, didn't think it's so important, or maybe he was just humorous. And this tradition of not liking OOP persists in functional languages and in functional communities. Certainly, not all functional developers hate OOP, but those who do it very, I would say, foundationally. They do it passionately, or not sure what word will be correct here, but they do it very, very loudly. I would like to make a counter argument to that. This argument will be: we've spent too much time learning how to create correct FP programs. Now we should switch to useful ones. Because correct programs are not in demand in our field, are not in demand in the industry. The only thing that matters is whether those programs can solve business tasks, whether those programs can be useful for some cases, maybe not all, maybe not entirely correct, but the user generally doesn't care unless the program is buggy as hell. Then certainly, but time to market means more. And again, this is another huge social aspect of software engineering. So we not only have technical aspects of software engineering, but also social ones. And social ones are very important, and they are important for programming languages, because programming languages as a tool are intended to address technical problems, right? But we also need to account social problems and social requirements. And if a language cannot do that, because it's a tool, communities and developers should do that. They should be social persons. This means they should understand business and its requirements and be able to talk on the same language as business talks. And maybe they do not need and should not do complication of their domains and pollution of those domains using mathematical terms or what terms the whole industry doesn't understand. Those research terms, terms from computer science, this all makes too much friction between business, industry, and functional languages. Yeah, and the first idea should be just be useful to business. Program useful programs. Well, software engineering is kind of a navigation map in the field of unknown things that you need to program and make those things known and understand where to go and where you should not go, what are the risks. Software engineering is a risk management activity as well. It's many things, but also risk management. That's it. That's it for now. That's it for today. Learn software engineering, program things, useful or not, that's up to you. I personally would continue developing software engineering discipline for functional programming and type-level programming. Actually, some folks say, "Oh, he invented software engineering, ha ha ha, for functional programming, ha ha ha. He didn't know about 30 years of software engineering and functional programming." Well, actually, if you follow my reasoning, you will see that I have a specific vision of software engineering for Haskell and for functional programming in general, and this reasoning is not quite presented in the field, right? Because folks are doing stuff that is not quite comprehensive, not quite practical, especially in Haskell. And this is a huge gap in software engineering. There are software engineering methods, approaches, practices, they are separate and it's a secret knowledge, but I do not invent software engineering as they say. I invent a methodology of software engineering for functional programming. And this methodology makes sense because it unifies the things. You can take it and you can build an application with a certain quality, with all the things you need to know, and you do not need to do research. And this methodology, I called it functional declarative design, is a part of software engineering, but it's not a part of scientific software engineering for sure. So if some says, oh, what he does is already done, no, for functional programming, it's not done. There are many other gaps, and my duty is to fill those gaps. So let's return to the previous slide. My Haskell profile. Well, you first probably thought that clown and joker, which are here, like there is a clown and there is a joker, do not belong to this list because, well, those clowns and jokers, what do they do here? They actually have some relation because there are notions in computer science, in abstract algebra, if I'm not mistaken, or maybe in category theory, that are called clowns and jokers, which is ridiculous, but it is what it is. Scientists are fun persons. There is monoid and there is paranoid. Well, paranoid does not belong to this list. Maybe we can call some notion paranoid, but actually it doesn't exist. At least it didn't at the moment of this list composing. So that's it. So thank you and see you next time. Bye.